Quotes on thermodynamics. One up here because it's talking about, some different people saying that if you haven't read Shakespeare, and scientists not reading, or engineers not reading Shakespeare, and then they're criticizing, their knowledge, broad knowledge in areas. And then, Dr. Ch.0, who is both a writer and a physicist, asked them what is the second law of thermodynamics, and then it was very cold, no pun intended. But so if you're an industrial engineer, chemical engineer, you're an English major, I think a lot of the great minds throughout history would agree that Shakespeare and the second law of thermodynamics are on equal playing fields, and you should know both. Now, you can argue with them, but if you are somebody who's going to be educated and get paid for your education, then I would suggest that you don't argue with those who have been successful based on that. You should learn from them. And so, I haven't read enough Shakespeare, but at least I'm familiar. But I would agree with this. Fine arts, some of the great works, are on equal footing to thermodynamics. So this is the quote that a lot of students, or some students, didn't like to hear. So thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. So some of you are taking thermodynamics for the first time, and you're going to feel like you didn't learn anything. Then the second time you go through it, you think you understand it, except for a couple points. And so this is how I felt the first and second time. And then the third time is usually when you're in graduate school and you learn more, or you take higher level thermodynamics courses. And then, you don't understand it, but you're fine with it at that point. So it's just one of these subjects that is not intuitive, and it takes time. You learn little by little by little. So I'm going to try to teach the course in a way that you get some foundational information and you build on that. And then I like this quote: "In this house we obey the laws of thermodynamics." So she was making a perpetual motion machine, and I'll have some lectures on perpetual motion machines later on. Okay, so what are the first, second, third, and 0th laws of thermodynamics? So if you've heard from other students that all you have to do is memorize the laws, no, that's not all you have to do. Where does this come from? When I was an undergraduate, a professor I really liked and respected was teaching thermodynamics, and he was saying, I can't stand when other professors are saying they're going to do something, or engineers, and they don't even double check if it violates the second law of thermodynamics. They don't even double check. And so I said, when I was an undergraduate, if I ever teach thermodynamics someday, I want all the students taking my course to know the laws. So this is my form of getting you to know the laws. So hopefully, when you're an engineer working on things, you know to double check if you are violating the laws of thermodynamics. Because if you're violating the laws of thermodynamics, it's not going to work. And if you find a way to violate the laws of thermodynamics, you will be a billionaire overnight. And nobody's become a billionaire overnight by violating the laws of thermodynamics. So my suggestion is, know them, try not to violate them. Your best bet is to let somebody else become a billionaire. So what is the first law? So there's a specific way to write it. There's a lot of details associated here, but I'll write it out. There is an equation of state of the system called the internal energy. And I'm just going to use a U. You can use E also. In the online portions I've used D, but U and E can be interchanged. So there's an equation of the system called the internal energy. In an adiabatic system, the change in internal energy and I'll just put delta U even though I haven't put that. So change in internal energy, delta U, is equal to the work done, I'm going to put in capital letters with the underlining bold, on the system. Okay. In a system, in thermal contact with the surroundings, the heat flow or absorbed called Q. So that's the heat flow or absorbed is given by Q is defined to equal the change in internal energy minus W. So you can rewrite it in different forms if you feel fit, but most likely when students try to write it in their own words, they mix up things and they start putting by here. They write this a little bit different. They don't say change in internal energy. They forget various things, and then when it comes to grading, I have to mark you off. So let the first time just be a memorization. The second time, try to write it in your own words. Then by the third time, you'll understand that there's some things you don't understand with there's a lot of meaning in all of this here. Okay, then there's some key comments associated with the first law. The first law does not describe the direction a natural process takes during a reaction. So if I have an explosive, it doesn't tell me the direction of the reaction. We know from other means the direction of the reaction, not from the first law of thermodynamics. It does not describe the direction of a natural process. First law doesn't give you that information. What it does give you, it tells you that that heat the first law does tell you that heat is a form of energy. Work is a form of energy. Change in internal energy, of course, a form of energy. Heat is a form of energy. That's the first law does tell you that heat is a form of energy. 100 years ago, that was very profound. Today, it's well accepted. And most of the time, if you ask somebody what is the first law of thermodynamics, they will tell you that it's a statement on the conservation of energy. First law, and so the first law is a statement on the conservation of energy. And energy can be neither created nor destroyed. So that's the first law. So that problem right there, maybe your first exam is going to be 7 points out of 100. So if you get it wrong, you automatically go, and you get everything else right, you automatically go from 100 to 95. I'm probably going to ask you on the second exam or other exams or the final, and you can do the calculation based off 20%, 40%. And so the laws are 25% exam 1, 25% of exam 1 times 20%, that exam 1 counts toward your final grade. So you're already saying that the laws are already worth close to 7% of your final grade. So if you don't know the laws, you're automatically pushing yourself, not getting close to getting A. Question?
Shouldn't it be energy cannot be created nor destroyed?
Can be neither created nor destroyed. Yeah, it's hard to write on here. Yeah, so energy can be neither created nor destroyed.
Excuse me.
Yes.
Can you please read the second?
This one?
No.
In
the first law. Yeah.
In an adiabatic system, the change in internal energy, delta U, is equal to the work done on the system. So I'll try to write a little cleaner on the next one. So on web courses, I've posted all of this stuff. So on web courses in the file folder, I have all the lecture notes and everything posted.
Are you getting all this posted?
They're always posted. Question in the back? No? What's that? It's handwritten, but it's cleaner. So that's the first law. Second law starts out very, very similar. Now, it says there is an equation of state of the system called the entropy. And I'll just put S here, even though it's not in the thing. So entropy is fine. I'm just showing you the symbol. So in an isolated system, the change in entropy is defined to equal the integral of delta Q reversible heat over temperature, where the change in entropy has to be greater than or equal to 0. If the systematic process is reversible, then delta S equals 0. Some key comments. So again, here I have this equation of state to the system. It's important that you write that. You might not understand what that means now. But later on, hopefully by the end of the course, you'll understand the real reason for that and the kind of the profoundness of it. Yes? That's REV, reversible. So reversible heat. Yes?
Is that dQ reversible?
There's a delta here, which is equivalent to delta. It's equivalent to D. So the D in calculus and the delta in calculus, they're coupled with conservative and non-conservative processes, forces. So this is more exact to use the delta instead of D. If you want to put a D there and not worry about that aspect of it, that's fine. Yes? Yeah, so the change in entropy is defined to equal, for an isolated system, the integral of dQ reversible over T. So it's an integral. I mean, I can write it as this. I'm just mathematically I'm not explicitly stating the non-conservative conservative aspects of heat, of a conservative force and non-conservative force. Yes?
What's the word after process is in the last sentence?
Yeah, if the systematic process is reversible, then the change in entropy is equal to 0. So this reversible statement is for an isolated system, which we'll get to a little bit more. So I'll try to write the next one even cleaner. So the key comments related to the second law, one is the second law does dictate the direction a process takes So the first law doesn't tell you the direction a natural process takes during a reaction. The second law does define you the direction of the process. And it defines the direction of a natural process in terms of an increase in entropy. Yes. Summarize the laws of thermodynamics. You don't have to look it up in a textbook. It's built into your intuition after years. You're less likely to violate one of the laws when designing something or engineering something later on. Another key comment is that entropy is a measure of disorder, and I call that the pessimistic view. Another key comment is instead of the pessimistic view, you can say the entropy is a measure of the number of options, and I call that the optimistic view. So there's a few different ways you can look at it in terms of an optimistic view or a pessimistic view. So sometimes people describe entropy as a measure of disorder, a measure of chaos. You know, that's not exactly right, the chaos aspect, but sometimes people say that. I like to think of it in the optimistic view as a number of options. So the second law says that your life is always going to provide you more options. Sometimes you might not like those options, but it provides you more and more options. It provides physical processes, more and more options. That's the natural process, is to increase the number of options. You could look at it negatively and say, increase the amount of disorder. Any question? And the fourth key comment is S is equal to KB, Boltzmann, that's Boltzmann's constant, times the natural log of omega, where omega is the number of options or the number of accessible states. So you need to be able to reproduce all of that. You don't understand a lot of the details now. By the end of the course, hopefully you understand why every single word's written the way it is. Then you're going to know the laws of thermodynamics later on. The third law in a homogeneous system, in complete internal equilibrium, the entropy of the system approaches 0. As the absolute temperature approaches 0. Okay, so I can put S approaches 0 as T approaches 0. Okay, related to this expression here, you need to write all of this. S equals 0, which implies that 0 equals kb natural log of omega, which implies, because this is a constant, that 0 equals natural log of omega. When does the natural log of something equal 0? When this is equal to 1, which implies that omega equals 1. Therefore, as t approaches 0, omega approaches 1, or the entropy approaches 0. So as you approach absolute 0, there's only one option. So if we were to cool this classroom down to absolute 0, there would only be one option for every single one of us. That would mean we basically all become the same thing. Of course, we're not going to cool all of us and the whole room down to absolute 0. Yes?
How do you read the little dots that are forming?
Oh, this I just put therefore. And I'm not going to write out the zeroth law. I'll just say it in words. If two bodies are in thermal equilibrium with a third body, then they're in thermal equilibrium with each other. So everybody gets that one right. So you can look at the lecture notes on that. So I want to touch back on this form. So this is kind of the physics way of looking at entropy. Do some pictorial representation of that. So omega is the number of accessible states, or the number of options, and I have this expression. So if I have a single molecule, what are the options of this single molecule? Atomic hydrogen, in terms of translational degrees of freedom. How many degrees of freedom does it have? Yeah. 3 degrees of translational degrees of freedom. Now I take molecular hydrogen. Now there's a bond between the two hydrogen atoms. How many translational degrees of freedom? 2. Okay. So what is a translational degree of freedom, given that somebody said 2? Think of it in terms of Cartesian coordinates. X, Y, and Z. Can this go in Z? No? If I just consider a dumbbell, it can go up and down, back and forth, and right and left. So it still has 3 translational degrees of freedom. Now I'm not considering here boundary conditions influence on translational degrees of freedom. Now, of course, you could change the system at which this molecule is in, and you could restrict, say, some translational degrees of freedom. We're just talking about that a molecule not influenced by its surroundings. What are the options it has? Now, of course, when you change boundary conditions, you change the system, you change the number of options. That's where thermodynamics comes into play. You as an engineer are changing boundary conditions. You're adding energy. You're changing options. Okay, so 3 translational degrees of freedom, rotational degrees of freedom. So it can rotate this way, and it can rotate this way. Rotating like this, I don't know if it rotated because of the electronic Coulomb symmetry of a hydrogen atom. If I were to put something over here, then I could distinguish. So if I bind something, so this only has 2 rotational degrees of freedom. Now vibrational, so my molecule, it can vibrate. How can it vibrate? Like this. It can't. If I put a spring between 2 masses and I pull them out, how do they vibrate? Back and forth. That's one of them. What's the other vibrational degree of freedom? Right? I can't distinguish between this one. I guess you could say this one, but it's hard to distinguish between it, so it's more this one. So 2 vibrational degrees of freedom. So if I look at the total options of this one has 3 options, this one has 7 options. Now if I take a water molecule, so now I've put something in the center here, and translational degrees of freedom 3. Rotational degrees of freedom. Now I can rotate like this. I can rotate like this. So now this other one with the hydrogen where I was rotating, now I can distinguish between that rotation. So I have 3 rotational. And now there's 4 vibrational degrees of freedom, so I can do things like this, like this, like this. And then there's another one I always forget off the top of my head. But you have all these dance moves, I guess you could say, for the water molecule. And so there ends up being 4 vibrational. So like this, like this, like that. And then there's another one.
Up and down?
I just did that one. Anyways, I'm just shaking my arms around. So there's 4 vibrational degrees of freedom. And so then if I look at a water molecule, how many options does it have? 7, 10. 10 total options. So you can see if I make things more complex, what happens to the number of options? I add more students to a class. What are the number of options of emails I get? Entropy supports my class in many ways, whether I like it or not.